This is the first part of the chemistry summative, and in this part there are three simulators: the Boyle's law simulator, the Charles law simulator, and the Gay-Lussac law simulator. So for the first simulator, as you can see here, the Boyle's law is stated that if the temperature is constant, the pressure increase and the volume increase. So I make the temperature constant at 221K, 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 221K. And as you can see, when I put my volume as 10 nanometer, the pressure is 12.8. And when it decreases, it also decreases. So this is decreasing. And I just changed this to nanometer and to liter. And as you can see, the graph is negative, non-linear. It's going down. Now, for Charles' law, it states that if the temperature increase, the volume increase if the pressure is constant. So, I make the pressure 2400 kPa, all of them. And as you can see, I up the volume from 10 to 730, it ups from 334. Same thing. So it increases both of them. So for this one, the graph is positive, the slope is positive, non-linear. Now for the last one, Gay-Lussac law. It states that if the temperature increase, the pressure increase if the volume is constant. So I make the volume constant as 10 nanometer, the temperature as 297, and the pressure is 1,555. And as it increases, it also increases. And the slope is a positive linear slope. And that's it for part 1. Okay, now this is the second part, and I'll use this balloon, measure at 46 centimeter. And first I'm gonna put it to I put in hot water. Okay, now the temperature is around 70 degrees. I'm gonna put this balloon in. And I'm gonna cover it. And I'm gonna leave it here for 10 minutes, and let's see how the balloon size gonna change. After I put this balloon in hot water for 10 minutes, it actually increased with 1 centimeter. And so now I'm gonna put this in the refrigerator. And this is about 5.3 degrees. So I'm gonna put it in here for 10 minutes. As you can see, after 10 minutes in the refrigerator for 5 degrees, it actually reduced to 45 centimeter. Actually reduced 2 centimeter. And now I'm gonna put it in the freezer. Degrees, so it's a little cooler down here, and I'm gonna put it in here for 10 minutes. So I'm gonna put it, of course I can. Take the water out and see you in 10 minutes. Put in the freezer at 10 degrees for 10 minutes. It actually increased only a slight of 1 centimeter. So that's it for the data. And I move on to the experiment. I will compare the experiment with the simulator. And as you can see, it's rising from when the temperature is rising, the volume is rising. So as the temperature rise, the volume rise. So as you can see, the concept of Charles' law works for the experiment too. Part 3 of the chemistry summative. Now, in this assignment, I need to create a weather balloon. So in order to create a weather balloon, I need to know where the weather balloon is going. And it's going to the ozone layer, which is located in the stratosphere about 20 to 30 kilometers above the Earth. So with this information, I know and I can create my balloon. And I decided to make the balloon as 600 grams in size, and I have a payload of 2300 grams, and I have a positive lift of 100 grams. And the required helium in cubic feet that need to go up is around 107.85 cubic feet, and the estimated altitude that it will explode is around 26,000 meters. And the average going up time is around 1.58 meters per second, and the time that it ascends is around 273 minutes. Now the question asks is how many moles of helium there are. So if I want to find the mole of helium, I need to transfer the cubic feet to liter to mole. So cubic feet is equal to 28 liters, and 1 mole equal to 22.4 liters. So I take cubic feet, this number, time with the 28.316 equal 3,554 liters. Then I take this, I time this, and I get the mole, 136 mole of helium that it required to go up. Now the next question is why the weather balloon explode at a certain altitude. And to answer this, we have to use Boyle's law. So before Boyle's law, we need to understand the higher we go, the pressure will decreases because there's less air at such a high altitude. To prove this, I'm going to use the Boyle's law. The Boyle's law states that if the temperature is constant, the pressure and volume is inversely proportional. The equation I will be using is P1 times V1 equal P2 times V2. So let's say I have 4 ATM, around 400 kPa of pressure, and I have 400 liter to start. But then the pressure dropped to 2 ATM or 202 kPa. What is the new volume? As I subbed it in, as you see, the volume increased double in size. So this worked with the balloon. When it go up, the pressure decreases, so the volume increases. It increases double size, which is more than a limit, and for sure it's gonna break. That's it.